All right, shall we start?
Yeah, I'm trying to get this away as well.
I just double click on it. On the screen, the main screen. We should be okay.
Okay, yeah.
All right. Hi everyone. So this is the very first seminar of the semester, High Energy Theory Seminar. We're very happy to have Jeremy van der Heiden from University of British Columbia. Jeremy did his PhD at University of Amsterdam, working with Eric Verlinde, who was your supervisor, right? All right, so we're very happy to have him. He's going to tell us about quantum chaos near the edge. He's going to be around today and tomorrow, so his office is over there if you want to stop by and chat with him. Please, Jeremy.
Okay, thank you, Nima, for the invitation. I'm very happy to be here and tell you about some interesting work that we've been doing at UBC and before at the UBA. Yeah, so my talk will be about aspects of quantum chaos, and specifically we will focus on a particular regime of quantum chaos that we characterize as edge physics, and we're talking about the edge of the spectral density here. I guess this project will tie in to some current themes in high energy theory related to low dimensional gravity and the interpretation of those ideas in terms of quantum chaos. It will be based on a couple of papers, so the talk will mostly be based on the last paper that came out this year with some people in the chaos community and Moshe Rosale, who's at UBC as well. But the ideas that led to that paper were already in some of the previous papers that I also listed. So those will be relevant as well for our discussion. Oh, no, it's not.
All I want to close that thing on the bottom.
Yeah. Okay, this is weird. Okay, yeah. So this will be the outline for today. So I will start with some motivation and some general ideas that I already mentioned, so the relation with low dimensional gravity. Then we'll go into quantum chaos, and I will show you a certain computation that we did that characterizes certain properties of eigenstates in a quantum chaotic system near the edge. I will show some interesting results there, and then I will move on to the interpretation in terms of gravity, and in specific, I will focus on two-dimensional gravity, where hopefully these ideas can be realized geometrically. So on the way, I will introduce a certain universality class associated to eigenstates near the edge, and the goal of this talk will be mostly to see if these effects are represented gravitationally, and if so, in what ways specifically. I hope I'll get there. So let's start with the motivation. So I guess these papers sort of fit into a general development that relates ideas in quantum chaos to certain ideas in quantum gravity. This has been going on for a while. There are all kinds of different directions one can study this interplay. And I want to focus on a particular example that has to do with two-dimensional gravity and random matrix theory. So maybe some of you have heard about that. It's sort of based on some ideas related to JT gravity, the SYK model, and I think we've developed by now sort of some reasonable understanding of this duality, and I want to sort of ask questions in that setting. So most of the standard measures in quantum chaos that people have focused on, especially in our community, are level statistics. For example, they're a probe for quantum chaotic features, and in particular also the spectral form factor has played an important role in this development. So today I want to focus on a slightly different aspect of quantum chaos, namely so-called eigenstate statistics. So instead of focusing on the eigenvalues, I want to focus on the statistics of the eigenstates. And as I was saying, I want to sort of address the question, can we think about these effects gravitationally in some way as well. So that will sort of be the motivation. So let's start off with a brief slide of quantum chaos. And yeah, I don't want to go into all the details. It's like a very big subject, but I want to sort of highlight some interesting features. I mean, some of you here work on quantum chaos, so these things might be familiar. But for those of you who aren't familiar with quantum chaos, I would say describe some universality class, I guess, of quantum mechanical systems that is associated to properties of the energy levels and excited states. And usually one thinks about it as some kind of effective description that emerges at late times in your problem. Sometimes it's referred to as the ergodic phase or the quantum chaotic phase. And one important feature is that, well, these universal phenomena that appear in certain quantum systems are well modeled by something that is called random matrix theory, which is a very sort of simple model, you could say, because it simply involves an integral over matrices H with a certain measure that I wrote down. And it's expressed usually in terms of a potential V of H, and this potential can have certain properties. So usually one considers certain invariant ensembles that have some kind of symmetry property. So today we'll mostly focus on ensembles that have unitary symmetry. So there can be some unitary operation that leaves the potential invariant, but in principle one can study different classes of random matrix theories that are interesting. Yeah, this is a typical model, I guess, that sort of resembles this late time physics in a way. And in particular, statistical properties of the spectrum, for example, they are in a quantum chaotic system, they're well modeled by RMT. And yeah, so some people might say it's a definition of it. I'm not sure if that's exactly capturing the full idea, but at least this is sort of an interesting model that captures many of the features that one wants. Yeah.
So late times for you means square root D? What is late time?
What do you mean by square root of what?
D.
Square root of D. So I guess, I mean, it depends on the particular question you're asking. So there are different time scales associated to chaos. So I think for me, I'm interested in like very, very late time chaos, which would usually be like, yeah, the Heisenberg time, I guess, where the plateau arises. One can study early time. Yeah. So like, yeah, yeah. There are other skills in the problem. You can also consider the Thulis time, which is also something that sort of appears in random matrix theory. But for our purposes, we're interested in very late time physics, where you actually are probing like the very fine-grained properties of the micro states. So yeah, so this is random matrix theory. If you've never seen it, and in particular. Yeah, what are certain properties of that model that are interesting? Well, for example, one interesting property is that the spectrum exhibits eigenvalue repulsion, which means that in this ergodic phase, the spectrum, the eigenvalues in the spectrum, they're not like completely independent, but they're correlated in some way, and that correlation sort of gives rise to a repulsion. So eigenvalues don't like to be close together. And this creates for you some kind of like crystal-like structure in the spectrum. So in some sense, the spectrum of a chaotic system is more ordered than of a usual system, as you can see. So on the right-hand side, I've drawn some impression of the eigenvalue repulsion spectrum, and then on the left there's a spectrum of a non-chaotic system. And in particular, you can associate a mean level spacing to the spectrum, which means that there is a typical distance between two eigenvalues that I've called delta. Yeah.
Is this eigenvalue reflecting the same thing as no level crossing, or is that different?
I think it's a slightly different concept. Yeah. But indeed, of course, like when two eigenvalues cannot coincide, there cannot be any crossing, I guess. But it's something that we will address, I guess, because this crossing is usually associated with like certain perturbations that you can do, and we will study similar kind of perturbations to the system. So eigenvalues can start moving around, I guess. And as I mentioned before, the one probe for these kind of features is the spectral form factor, which you can express in this way. So it just involves a Fourier transform of the spectral correlations, and as you can see, one interesting feature is that there's a difference there. So EI minus EJ, which is the typical distance between two energy levels. So when I take T to very large, what will happen is that the effects of these energy differences will become very manifest in this correlator. So for example, when there are no degeneracies, this will be some kind of chaotic phase, I guess, that appears that you can see at very late times. So this is an object that has been studied a lot in the chaos community and also more recently in the high energy community. But for today, I want to sort of focus on a slightly different quantity.
So just one.
Yeah.
So this eigenvalue repulsion comes from the fact that in your integral over H, you're integrating over the unitary group.
Mhm.
So it comes from the unitary group part of the integral.
That's excellent. Yeah, that's an amazing, good observation, I guess, that if you perform this integral, one way of doing it is like diagonalizing your matrix H in terms of eigenvalues. But of course, there's some choice of basis that appears, and the van der Monde, I guess, of that transformation will lead to a factor that involves energy differences squared, I guess. So it's like the van der Monde determinant that gives you the eigenvalue repulsion. So so if you take a different ensemble, that will have different, that term will be different. So the eigenvalue repulsion will be differently manifested. So yeah, for today, I want to sort of focus on a slightly different quantity that one can compute in chaotic systems. And in particular, it's associated to the eigenstates. So this has been a pretty recent development, I guess, in the chaos community, where people have started to become interested in these kind of quantities. So I put some references. But the general idea is that you take your quantum chaotic Hamiltonian and you deform it by some external parameter lambda. As you can see, you add some perturbations, and that also deforms for you the eigenstates in a certain way. Now, what you can do to study these perturbations is to define a metric or a distance measure on the space of eigenstates. I've written a formula for it. It's not super important. I mean, there's a reason for why this appears in this way. It's related to what is known as the fidelity, I guess, of the two states. But for now, I just want to mention that there is some kind of metric that takes this form in terms of what is known as the quantum geometric tensor. And this is a very explicit formula because given the perturbations, I can just take these derivatives and take the overlaps, and it gives me some formula for the metric. So for people who are familiar with this is called the Fubini-Study metric. And yeah, it's a well-known quantity in the quantum information theory geometry, I guess, that one can associate. So for simplicity, today I want to focus on the diagonal part of that metric, which has a sort of a simple expression in terms of the perturbations and the eigenvalues. So recall this H alphas are the perturbations that I have, and these psi n's and psi m's are the original eigenstates. So yeah, you can show that this quantity, if I evaluate it for these perturbations, the diagonal part will look like this. And this is a very explicit expression. I mean, it looks kind of like perturbation theory, I guess. So maybe it resembles some things you know about perturbation theory, quantum mechanics. But for now, I want to highlight two things. Namely, first of all, there's a dependence on the eigenstates through the numerator, and then there's also a dependence on the energy level differences through the denominator. So it probes both eigenstate statistics and also the eigenvalue statistics of your system. Okay, so these G alphas are random variables because these H's are in general they have some kind of statistics associated to them. So I want to consider the following distribution where I sort of define the distribution of the G alphas in terms of a variable G, and I want to perform some averaging over H and H alpha. So in a general chaotic system, this averaging can mean a lot of things. So for now, I want to just keep in mind the matrix model discussion, and then in this case, this H is simply your matrix integral. And this H alphas also have some kind of distribution that you can choose for the perturbations. And this PG is like a quantity that appears in the chaos literature that people have studied, and it's in some sense a distribution of the fidelity susceptibility. And as I will show, it probes some features of the eigenstate statistics. Yeah.
So just naively, I would
Yeah.
have just that expression is very suggestive because if you had told me that H alpha are going to be simple operators,
Yeah.
local operators,
Yeah.
or integrals of local
Yeah.
operators, then ETH will tell
Yeah.
you that individual.
Yeah.
Is that the way that's going, or?
I mean, I'm not going to invoke.
Average over H alpha.
I'm not going to invoke ETH immediately, but like you can use ETH to give a rough estimate, I guess, of what they should be.
Another way of asking my question is that the philosophy of ETH is select H alphas.
Mhm.
These are local expressions.
Mhm.
But what you're doing is you're averaging over all H alpha. Is that correct?
Yeah.
So
Yeah.
your analysis is blind to locality.
Yeah, that's true.
But these quantum mechanics, they know locality.
In quantum mechanics,
Yeah.
there's also a notion of a simple operator versus complex operator.
Yeah.
Um,
But I think the philosophy is correct. Yeah. So yeah, so that's sort of the quantity of interest is PG, this distribution, and I want to sort of show to you how to compute this this thing in a. But yeah, there are different choices to make. So there are different scenarios that you can consider, and I want to consider 3 scenarios. The first one is well, where I take a distribution for H that is diagonal for diagonal matrices, which are randomly distributed, but there's no eigenvalue repulsion, because in this case, is as you were saying, the van der Monde determinant will not appear because I don't have this off-diagonal terms. So in this case, it will simply be an ensemble of integrable systems. So this will be my choice of like integrable model. And I want to see what does the quantity look like. Then the second case I can consider is where I take this this to be an RMT ensemble. And in this case, I want to consider the unitary ensemble, where I do have eigenvalue repulsion, and I want to see what is the answer. But then I will argue that there are actually 2 regimes, even in this RMT ensemble, namely, I can consider energy levels that are very close to the edge or very far away from the edge. So I haven't told you, but like these spectra have like edges, which are denoted by E0. And yeah, I can consider energy levels that are far away from the edge, parametrically far with respect to the level spacing, or that are kind of considerably like the same size as the level spacing close to the edge. And I will argue that these 2 regimes have different physics associated. So for example, this PG will have a different behavior as a function of G.
So in case 1, you're basically sampling, you're throwing random eigenvalues or random points on a line, or maybe on your interval, or whatever is there. So you expect the delta E's to follow a Poisson distribution? Is that what?
Yeah, for example, yeah. That's correct.
So that analysis doesn't care about near the edge or anything.
No, I don't think so. So yeah, I sort of want to flash the results, I guess, that we obtained, and then later on I will sort of maybe give more intuition how we computed them. So these are the results, I guess, that you obtained. So for the first, I mean, as I sort of look, I mean, this is not the full answer. I would like a little squiggle to sort of denote that this is sort of the leading answer for large D. And yeah, as you can see, there are sort of different dependence on G, I guess. As you can see, so first of all, they decay as G goes to infinity. So there's a decay. So it means that the large susceptibilities are suppressed in some way, but the suppression is different in each case. So for the integrable model, there's actually a kind of a large tail, which is governed by this factor of 3 to the power, factor 3 to the power half, which shows that there's a tendency towards large susceptibilities compared to the chaotic system. And if you recall, that's sort of partly because of this formula. You can sort of see it already from the eigenvalue distribution. So if this eigenvalue sort of can become very close, then this thing is enhanced in a sense.
That is for what ensemble of H alpha and what V of H?
So here we take the so the first one is just for a Gaussian ensemble, I guess, but where there's no eigenvalue repulsion. The second one is for the same for the Gaussian unitary ensemble, so there's their eigenvalue repulsion, and for the last one as well, but we take a different scaling, I guess.
But what is the ensemble of H alpha?
It's also GUE. So yeah.
GUE.
Yeah,
okay.
yeah. So in principle, one can take like more complicated ensembles, but yeah, it will be more complicated to compute the exact answer in that case. So it's just a Gaussian. Yeah, so hopefully, I mean, I will get to maybe a little bit more concretely how to compute this later on. But for now, I want to sort of say that integrable and chaotic have a different dependence on G, and the tails are kind of smaller. And for the edge case, there's even a different dependence on G, that different scaling, and that sort of scaling we refer to as a new universality class, which we called UFL, and it resembles yeah, I will come later to what is exactly the kind of universality that we find, but there is some kind of rigidity, I guess, in that, and I'll show you a picture of how it works. But there is some kind of rigidity in the eigenstate statistics near the edge, and it's because, of course, there is an edge. So the fact that there's an edge makes that the eigenstates, I mean, they can fluctuate, but there is some kind of hard edge that they can't move past. So it sort of makes them more rigid to external perturbations. That's sort of the intuition.
This is for large D, the dimension.
Yeah.
And if there are some assumption like G is smaller than D, or you can take this very large.
In principle, no. Yeah. So yeah. Okay.
Sorry, these
yeah.
are finite D answers or large D answers?
I think they're large D answers. Yeah.
So you've used saddle point.
Yeah, you use saddle. I mean, for this one, you use a saddle point, I guess. I will argue that for this one, the full answer I think the saddle point is not reliable because you're near the edge.
But
So
can't you do like this exactly? Because these are Gaussian integrals and samples from random unitaries.
yeah, that's right. But these answers are like in the large T. So there's more terms, I guess, that appear. Yeah.
And are you going to tell us about an interpretation of d to the power 1/3?
Yeah, that will become clear later. Yeah. So here's like a plot, I guess, that sort of shows maybe the general structure. So this is just some sample of like a random matrix, where you consider energy. Sorry, the state differences, I guess, different eigenstate differences, where we have a very small perturbation. And you can sort of see roughly from the picture that in the bulk of the spectrum, the perturbations can be quite large, while if you go near the edge, they sort of get suppressed. So that's sort of reflected in this fidelity susceptibility. But perturbations near the edge, they are more suppressed, and the eigenstate statistics there is more rigid.
Everyone
yeah.
defining what that, so psi, what is that delta psi? It's so it's the eigenvalue, eigenvector. Is that the norm of the yeah, what is it?
Yeah. So this is just sort of the wave function, I guess.
I'm not understanding. So
it's like the difference between the value of the wave function.
psi m of 0 and epsilon means what?
It's I guess it's the wave function. Like it's just a function, I guess. Yeah. I mean, I could show a little bit more. I mean, more detail how this works. But, yeah.
Okay, maybe we'll.
Yeah. Okay. So before I move into the details of how to compute this, I want to sort of move to sort of the main question I want to ask. So given this, these features that we saw, is there a way to understand them geometrically? And in particular, a concrete setting where I think we can maybe answer this question is in the setting of two-dimensional holography, where there is a somewhat precise duality between theories of two-dimensional gravity and RMT. And I will now explain what that means exactly and go through some of the details. But yeah, I mean, at least in this context, you might be able to say something gravitationally. So now we move away from the quantum chaos and move into some gravity things. So I mean, this is more of a review. So for some of you, this might be familiar, but I'll still try to go through it. So we've seen the JT gravity model before. Not everybody. So I'll just go through it slowly then. yeah, so gravity, of course, you can define in, well, in principle, you could define in any dimension, but it turns out that in 2 dimensions, it's a little bit more subtle. And one of the subtleties that appears is that the usual Einstein-Hilbert action that you can write down, and that's sort of the first term in brackets over there, is a topological invariant. So in 2 dimensions, if you have some manifold M and you write down this term, it will just be a number, which is the Euler characteristic. That's the Gauss-Bonnet theorem. So that sort of prevents you from having any dynamics, which is, yeah, kind of problematic if you want to define a theory of gravity. So what people do is they say, okay, maybe we need to have a more evolved model, and one of these models that people define is JT gravity. So instead of just having the metric, there's an additional field, which is called the dilaton field, phi, which is a scalar field, and you introduce an extra term in the action, which is phi times r plus 2. And that sort of generates some non-trivial dynamics, I guess, in the model, and yeah, especially in nowadays in the context of ADS2 CFT1, this has been a model that's been studied quite a lot. So yeah, as I was saying, the first term is just a topological term, so it just gives you the Euler characteristic times some large parameter S naught that is related to Newton's constant in this way, and it governs the semi-classical limit. So if I take S not very large, it means that I'm sort of working semi-classically. Then the second term involves the dilaton field, and then there's a boundary term, because usually in ADS50 we have a boundary for a manifold. In this case, this boundary is like a collection of circles, and it turns out that if we put this boundary term, we can generate some non-trivial boundary dynamics, which is governed by the Schwarzian theory. So yeah, I won't go into all the details of that, but yeah, there is some well-defined theory on the boundary. So why do we study this? Well, one of the nice things about this model is that the gravitational path integral for this model sort of makes sense, or at least there is sort of a sensible way to do it. I mean, it depends on your definition of sensible, I guess, but I can show you the arguments. So it turns out that if one does the integral over the fields phi and g, the integral over phi will simply, if you look at the action, will simply act as a Lagrange multiplier, and it will simply set r equals -2. So in that case, the integral will simply localize on constant curvature metrics. And in 2 dimensions, these are sort of determined by the topology of your manifold. So there are different topologies that can appear. And the idea is that each topology that appears gets a different weight because of the first term in the action. So the Euler characteristic sort of determines, is determined by the topology, and that term differs for each of these terms. So you get a sort of, the idea is that you get some kind of topological expansion for this path integral, where each topology is counted by this parameter e to the power s0. So in each topological class, there is still an integral over the metric that needs to be carried out. And that integral is some finite dimensional integral that one can actually compute. So there is some kind of like finite answer that comes out, and those are the set beta 1 to beta, I guess, that I defined. So those are really the quantum fluctuations of the metric, so you want. And in that sense, sort of this thing has a finite, well, I mean, it's an expansion, so you can ask questions, does it converge and stuff like that, but at least each of the terms individually makes sense. So in that sense, this is a theory of yeah, quantum gravity in some sense, because yeah, the gravitational path integral makes sense exactly.
So you still found a dimensional integral because the moduli you're integrating. I mean, yep. That's yeah.
I mean, it's an integral over the moduli, but in principle, there are like a finite number of parameters that specify it. So you can.
But don't you have so BIs are infinite of them, right?
Sorry.
Oh, this is a partition function associated to fixed manifolds.
Yeah, fixed manifolds.
So you're not summing over all topologies into that. Okay,
No, I'm just trying to say, like, given a fixed topology, there's a moduli space that has a finite volume, I guess. So yeah.
Right. You're not summing over topologies.
No.
Sorry.
Yeah.
What's B?
Yeah. So I didn't introduce it. It's I didn't. Yeah, because it's sort of. I don't think there's a board I can.
Oh, they used to do boards here.
Yeah.
They removed it.
I could I can maybe explain it later,
Okay.
maybe at the end or something, in more detail. But for now, the idea is that this this surface is like it's like a Riemann surface, and it turns out that the moduli space can be decomposed in terms of like cycles. So if there turns out to be like a specific set of cycles that you can define on your Riemann surface, and the moduli space can be decomposed as like a sort of in terms of these variables, and those are these variables pi. There are some kind of cycle lengths that you have to integrate over.
Well, the pair of pants decomposition.
Yeah, it's a pair of pants
So you take the
decomposition.
Riemann surface, pair of pants
Yeah.
decompose it, and the
Uh,
moduli.
Yeah, and this VGN is sort of the integral over over the internal manifold. So it's some kind of finite volume. And this observation was quite nice because the fact that you have an expression for the path integral allows you to actually ask questions about it. And one of the interesting observations that came out of this computation is that it turns out that there's a very intricate structure in this path integral. So in particular, different terms in this expansion, they correspond to different topologies, but it turns out they're not completely independent. So it turns out that there is some kind of recursive structure within this expansion. So different terms are related to each other in some way. And sort of uncovering these relations was done by Mirsakani, who's a mathematician. And she found a recursion relation for the moduli space volumes. And one interesting observation, I think, which was kind of crucial for many of the developments that are now still going on, is that these recursion relations are actually a manifestation of what are known as topological recursion relations, which govern random matrix integrals, or even more generally certain systems that one might study. And in particular, this kind of identification allowed people to make a conjecture, I would say, or some, namely that this gravitational path integral that one does, these contributions, correspond to certain computations in the microscopic theory that are like averaged, as you would do in a random matrix theory. And in particular, each term in the gravitational path integral agrees with a term in the expansion of some double-scaled random matrix integral. And the number of boundaries sort of specifies how many observables I put in the correlator. So this was kind of a very bold conjecture, I guess, because it gives a very new perspective on what ADS-CFT is in this case. Because normally in ADS-CFT we just have like a single boundary theory, and we have like some bulk computation that sort of matches that. But here we're saying, okay, if I include higher topologies, these things are not dual to like maybe a single theory, but to an ensemble average of theories. So this was kind of in a sense the proposal.
Would you mind saying what you're calling with conjecture?
Well, I mean, because so the thing you can say, I guess, is that these terms agree, but then you want to say make a physical statement, right? So you want to say, okay, this matrix integral computation that you can do to obtain these things actually corresponds to something that is that happens in a microscopic theory.
Ah, I see. But the equivalence of GT path integral with the random matrix model, that's exact.
That's exact. But I'm just trying to. I mean, I think that sort of maybe already existed in some sense. But I think what they were trying to say is that it's something like actually physical, or at least it tells you something physical about the microscopic theory. But I think that's, I mean, the interpretation is maybe still not exactly clear. So I guess the interpretation might be that the gravitational path integral doesn't compute exact quantities in the microscopic theory, but maybe average quantities. And higher topologies that you can add to the path integral sort of gives you more fine-grained information. So one interesting thing that you can compute is if you have two boundaries, there is a contribution to the Euclidean path integral in JT that is like a trumpet. And the trumpet should correspond to a correlator in the matrix integral that looks like the thing on the left. In particular, this is precisely the quantity that will compute for you the spectral form factor, in a sense. So we're saying that the spectral form factor in the matrix integral sort of is computed in gravity using this double trumpet, and in particular, it will give you the features of the spectral form factor that you want. So this double trumpet will give rise to eigenvalue repulsion in your model. Yeah.
So, with the inclusion of higher topologies, does that like have does the gravitational particle become like if I include all the topologies, does that become exact?
You mean does the average go away?
Yeah, like does it compute the exact quantity?
Yeah, that's a very interesting question. Well, I mean, it's something I'm sort of going to address, I guess, later. So I think for example, what we already don't understand is sort of the plateau feature of the spectral form factor. So this happens at late times, but it's not like the exact answer still. It's still averaged, but it's still a feature that you should be, that is sort of not captured already by this topological expansion. So you might want to say, okay, if I complete this topological expansion in some way, maybe the average goes away or not. And I will sort of explain now that it doesn't go away. I mean, I think it's still there.
But the naive sum blows up.
That's right. Yeah.
Yeah, the naive sum blows up. It needs to be completed.
Yeah.
It's just literally sum no, it blows up.
Yeah. So one of the features, for example, that is kind of special is that like if you compute the spectral form factor in like a quantum chaotic theory, it will have erratic behavior. So it will have like fluctuations. And the question is, can you capture that in gravity, for example? Well, you can't with this topological expansion, but maybe the completion you can. So that's those questions I now want to sort of address, I guess. So yeah, how do we go beyond the topological expansion of the gravitational path integral? Well, I mean, we've done a proposal for that, I guess, a couple of years ago, where we say, okay, we need a sort of a more extensive framework to incorporate this, and we call this like universe field theory, which is maybe a kind of a grand name for some. I mean, but you should imagine that these things are, in this case, are two-dimensional universes, so they're just they're sort of manageable. And these two-dimensional universes, like they, as we saw, they can form sort of non-trivial topologies like this. So one of the observations that people made, and we made as well, is that this structure, because it's three-dimensional, looks very, very similar to the things we look at in string theory, where one has a string that sort of propagates through a target space, and it forms different world sheets depending on the kind of interactions that appear between different strings. So this is, for example, a single string that can maybe make a bubble and like come back to itself, or if I have two strings that come together. So in string theory, we sort of know how to deal with these things perturbatively in the interaction. But then actually in topological string theory, which is a particular sector of string theory that is more manageable, we actually know how to sort of resum this expansion and actually describe this in terms of a field theory. So our proposal was maybe, because this is two-dimensional, we can maybe formulate a similar structure for JT gravity. So yeah, topological string theory forms a natural framework to incorporate this completion. And in particular, we identified sort of the target space that one needs for that. So this is kind of technical for those of you who haven't seen this before. But I think the main message is that we can actually think about this universe that sort of these different topologies as a string world sheet in a certain way. Yeah, the details of the construction are here. I'm not sure I want to say like a lot about it because it's a little bit technical, but this it turns out that this target space is 6-dimensional because it's topological string theory. So there's a 6-dimensional target space, and these strings are propagating there. But it turns out that we can describe these interactions in terms of a field theory that lives on the target space. In terms of a scalar field phi, and this phi sort of generates for me the number of boundaries. So each phi sort of gives me a boundary, and then when I set the number of boundaries fixed, the interaction term, which is a cubic term, will give me all possible ways of connecting these boundaries with each other, as one would do in string theory. So this field theory has an expansion in terms of Feynman diagrams. And it turns out that yeah, these terms in these Feynman diagrams, they compute like these surfaces, I guess. So the precise statement is that each of the terms in the gravitational path integral correspond to a computation in the field theory. So I need to do the field theory computation, and I need to pick out the correct Feynman diagrams, and they would compute for me the term in the gravitational path. And this, yeah.
Do you mind going back to this slide?
Yeah, yeah.
Oh. The field theory is just free massless boson plus a cubic term.
Yeah.
If you flow towards the infrared, what happens?
So I think it's a CFT, I guess.
Deep in the infrared
yeah.
is the CFT.
Yeah. Yeah.
And is that the U1 current algebra?
Yeah, I think so. I mean, yeah. So there is so the computation here is you can write down a path integral formulation, but I think the computations you usually do are in terms of like an oscillator algebra. So it's more like a CFT kind of computation, I guess, where you have some, yeah.
Yeah, I'll ask you later.
Yeah, yeah.
Thank you.
Anyway, so I guess the conclusion is that this sort of universe field theory sort of, yeah, it allows for you to reproduce all these different terms in the gravitational path integral that are sometimes called wormholes because they connect different boundaries, or baby universes because they correspond to like little universes that can split off. But it contains more. I mean, it doesn't, the perturbative expansion matches the gravitational path integral, but because it's a string theory, it contains more degrees of freedom. So for example, it contains open strings and also deep branes. And these can be used to sort of capture more fine-grained information about the underlying microscopics. Are there any questions about that?
Can you go back?
Yeah.
One, right?
Yeah. Yeah. Okay. So yeah, now I want to sort of see, can we sort of think about this universality class that we defined near the edge of the spectrum in terms of these kind of ingredients. So the first observation, and this is also a little bit like how do you compute actually this quantity? Well, the first observation you can make is that this PG actually can be rewritten in terms of a ratio of determinants in this way. And I mean, that requires like maybe a page of it's not like a few calculations, I guess. So you can write it as a Fourier transform of this SFS, and then that reorganized in terms of a ratio of determinants, where this beta sort of determines whether I'm in an integrable chaotic case. So we will focus on the chaotic case for now.
Oh, sorry, the determinants are there because you had the Gaussian, the GUE ensemble.
Yeah, yeah, that's right.
Is there a simple way of seeing why one of them is 1 over determinant, whereas the other one is determinant? Because you get, I would have thought you get, yeah. There's some sort of a like a way of thinking about it in the language of maybe.
Yeah, it's just a Gaussian integral in a sense. So if you look at the integrals you have to do, there will be Gaussian integrals.
That's why I'm surprised why you get determinant on top.
Yeah, that's right. So you will initially simply get the determinant in the bottom, but then you get let's see, you get a term from the eigenvalue repulsion that will reorganize into a determinant, which will be this beta factor that will be from the eigenvalue repulsion term, just from the from doing the average. And there will be terms coming above because I get things which are like 1 over the energies, I guess.
Another asking one question. Is there BRST way of doing this quantization?
What, sorry?
Is there a BRST way of doing it?
I'm not sure. I mean, I don't know. But I'm just trying to say like this PG quantity has like things that are going like 1 over energies. So there will be 1 over energies in the bottom, and there will be energies in the top as well because of that. I mean, I can show.
Good.
Yeah.
Oh, good. Yes, good.
So
So
yeah.
one more thing.
Yeah.
Xi's were. Do you want to remind us what Xi's were?
yeah, they weren't here before, I guess. I think we introduced them as a regularization, I guess, because of yeah, what we'll follow. I mean, we will identify these determinants with like certain branes, and Xi's sort of determine the position of the brane. So in the end, we want to make them coincide. But the computation is easier if you first separate them. Yes.
They're real variables.
Yeah. Well, I mean, they have. You can give them some imaginary part, but it will be infinitesimal. So it will be in principle just real variables. So yeah. So now we're back in a setting of chaos because we're simply computing this thing in a chaotic system, and it turns out that quantities like this, correlation functions, which are ratio of determinants, they can be computed using what is called the supersymmetry method. So it turns out that I can write a correlator like this in terms of a superdeterminant. So the superdeterminant simply makes sure that I get a number of determinants in the top and the bottom, depending on the signature, I guess. So that the bosonic ones come in the bottom and the fermionic ones get into the top. And that we organize this computation in terms of a Hilbert space that has two different components to it. It has a flavor component, which is called the flavor space. So it governs the number of determinants that I have. And there's a color space, which simply is the Hilbert space of the Hamiltonian cell. So it's d-dimensional. And this operator has a certain certain symmetry, I guess. Namely, it turns out that if I look at this quantity and I average over H, it will project me onto what is known as the color singlet. Yeah.
What are the Y variables? What is, I guess, I'm confused about N and M.
They're just energies, I guess you could say, but in our case, they might have some non-trivial dependence. So in our case, they will be like this combination or this combination. They're just some complex variables.
And when you did this integral PG,
Yeah.
you got something very specific. Two determinants downstairs,
Yeah.
and two or three or
Yeah.
four
Yeah.
upstairs.
Yeah.
But you just switched to a setup where you have n upstairs.
Yeah. I'm just saying something more general, I guess. I mean, this is like a more general structure.
Okay. But
yeah.
we don't.
But in the end, we will specify to like n equals 2 and n equals 4, I guess.
So your flavor is fixed.
Yeah. Your flavor is fixed. It's fixed by the correlator.
Plus beta or something.
Yeah. But the color can be large or small.
Yeah.
So one of the crucial insights of both Afetov and Wigner, like when they were studying this, was that in chaotic systems, it turns out that this correlator has a certain duality, I guess, which is called color-flavor duality. So by integrating over H, we will pick up in this correlator, you could say the coherent phase sector of the theory, where the transformations of H sort of they get projected out, and in the end, I can write everything in terms of a flavor sector of the theory, which I wrote down on the right hand side with an integral over A. And in this random matrix ensembles that I'm studying, this is an exact duality. So I can write the matrix integral for this correlator in terms of another matrix integral over a finite dimensional matrix A that is now a super matrix, and it has the same potential, so it has the same measure, but the determinant I'm computing is different because I've moved the H is now on the flavor sector. So this is called color flavor duality, and it's something that you can show in like this matrix ensembles exactly. And for a general quantum chaotic system, you have to check it, I guess, that it's expected to be true because of this yeah, this averaging that you do. So we can use this now to our benefit.
Can I?
Yeah.
So what's the interpretation of A here?
A is like a Hubbard-Stratonovich field, I guess. So it's like
But there's no like a simple chaos it's just a mathematical trick.
it's like a. I mean, I will give maybe some interpretation a little bit. Yeah, I mean, it relies on writing these determinants in terms of bosonic and fermionic integrals. And so you can write a determinant as a fermionic integral over Grassmann variables. You can write inverse determinant as a bosonic integral. And then you if you integrate over H, you will get bound states.
Yeah.
And those are precisely the A fields. So they're like bound states of fermions and bosons.
Right.
And then you can integrate out the fermions and you get this A as like a Hubbard-Stratonovich field. And
Yeah.
so in the end, I get the following flavor matrix theory representation of the same quantity. And as you can see, it doesn't involve any averaging over H anymore. It's now involves an averaging over A. And in particular, it's A is a low-dimensional integral, but also the thing I'm computing, this determinant, now takes a very simple form because of the color isotropy, the superdeterminant simply becomes an exponential of a supertrace. So in the end, I've written this complicated correlator of like determinants in terms of an integral that allows me to have like a stationary phase approximation. So the parameter d that I had before now appears as a constant in the theory. And this is what people sometimes refer to as like an effective field theory for chaos, because yeah, it looks like, well, it's a field theory associated to some symmetry breaking that I will not go into. So maybe I'm a little bit short on time, so I will try to get to the main point, I guess. So it turns out that if you go to the edge, so this thing is just true anywhere, I guess, in the spectrum. But if you go to the edge, it turns out that this matrix integral here reduces to what is known as a Kontsevich matrix integral. So you get a cubic term and you get some term which multiplies the source y. Yeah, this is sort of what we refer to as sort of the effective description of the edge. So why do we get this cubic term here? Well, since near the edge the spectrum looks like a square root, you can sort of see that some area integrals should appear, because yeah, the edge physics is related to this area integral. So this is some kind of like matrix variant of the area integral. It's not exactly the Kontsevich integral that Kontsevich wrote down, because this A is a supermatrix, so it's like a supersymmetric version of that. But it has a similar kind of diachromatic perturbation theory, and it can be described in terms of this causal symmetry breaking. So already from the perturbation theory, in terms of like these cubic diagrams, you can sort of see the matching with gravity.
So what does it mean, causal symmetry?
Yeah, it's I don't think I have time to go into it like completely, but it turns out that you can obtain this action simply from symmetry breaking arguments. So it turns out that this correlator has some symmetry that is explicitly broken by the y's, I guess. But because the y's are usually energy differences, it's kind of small breaking. And it has to do with the causal structure of this correlator. So I can sort of yeah, I can sort of act on the flavor space by GLMN. But then if I actually perform the integral, I will get a saddle point that breaks the symmetry to like a subgroup, and that symmetry breaking has an effective action to it, like you would have, for example, just in standard model physics, I guess.
So it's an exact symmetry of this expression that the saddle point breaks.
It's well, I mean, it's so it's already broken by the energy. So by the y's, it's already broken, but the y's are usually small, so it's like a small explicit breaking. So it's like an approximate symmetry, but then it's spontaneously broken by the solution.
Can you say what the symmetry is?
So the symmetry acts simply on the flavor space. So it just maps all the determinants. So it's GLMN. So if you look at this operator here, I can act on it with like a GLMN matrix, just by conjugation.
So M times N? GLMN.
Yeah, it's like the supergroup GLM.
Oh, supergroup,
bar.
yeah.
Sorry, GL.
Yeah,
And I can sort of apply that here, and it's symmetry indeterminate. But then if I actually I can
no, it's
yeah, if I had the, maybe I can do it on the board, but there's some simple examples where you can sort of explicitly see it.
Yeah.
But in that way, you can obtain this action simply by sort of symmetry breaking arguments. Like you would, for example, find the pine action or something. And
That actually like responds to some Goldstone boson.
yeah, it's a Goldstone, but the soft mode, I guess, or the Goldstone boson mode that appears. So yeah, so now if we go to the example of the PG, I guess, or the fidelity susceptibility, as a ratio of determinants, I can write it like this. This is universal form, where now this y sort of specifies these parameters I have. So it simply corresponds to the source of this Kontsevich model. And given this form, I can just perform the integral, because I can simply go to like the diagonal basis. I have some angular matrices, and then it turns out that supersymmetric matrix integrals like this are just exactly, you can perform them exactly.
for any D.
Yeah, for any D. Yeah. Yeah, so you can also approximate it by a saddle point approximate what you want, but this one you can actually compute exactly. And that sort of gives this, yeah, sort of the reason that you get the d to the power 1/3 is because of this array structure, I guess. Anyway, so maybe I will try to finish with the, so this is just a computation you do, and now I think that representation allows us to interpret it geometrically as well. So it turns out that, as I mentioned before, in this universe field theory, because it's a string theory, there's more degrees of freedom. So for example, there are branes that I can insert in the geometry. And it turns out that these branes, yeah, I can represent them as vertex operators. It's not really important. I just wanted to flash like this formula, namely that correlation functions of these branes we have computed precisely give a similar kind of super integral. Just from the universe field theory computation. Yeah, the superstructure comes because I have both branes and anti-branes. So this is something that happens in topological string theory. So given that result that we already obtained before, it's natural to sort of identify this quantity, the fidelity susceptibility quantity, in terms of a certain configuration of branes that one can insert in the target space geometry. And sort of this is some kind of heuristic picture to have in mind. So this is the target space where we have some branes that are represented now as little lines, I guess, are one-dimensional, but in the geometry they're actually two-dimensional. I have like these JT universes that are like moving around that runs construct for me the topological expansion of the path integral. But then there are also open strings that exist in this geometry, and those are the ones, their dynamics give me this quantity, I guess. So anyway, I mean there are some technical details and but I think that's sort of the general picture that we found, is that to capture this eigenstate statistics at the UFL, we need to have like non-perturbative brane physics, which is not unexpected because I guess eigenstates, like, they probe very fine-grained information, I guess, about the theory. Yeah.
My question. So the expression that you found by doing these Gaussian
Yeah.
random GUE integrals had a particular form, right? Two denominators downstairs, and depending on your ensemble, GUE I think was like 3 or something upstairs, right? That in this picture translates to, so that number 3, the beta, translates to the group GLMN.
Yeah.
So that is reflected in this universe field theory. How exactly?
It's a gauge field of the brain. So yeah. So it's like
flux number or something.
Well, I mean, so it's a number of branes. Yeah. So it's a number of branes, but then of course the group GLM is just because I have a stack of them. It's just the gauge field associated to the.
So it seems like a particular number of branes and a particular number of anti-branes.
Yeah.
If you increase them, are you gonna land on expressions that correspond to integrals of other non-Gaussian potentials?
Yeah, perhaps. Yeah, I mean, we haven't done that, but that might be the case. Yeah.
Wow. Okay.
Anyway, so yeah, I mean, this was some kind of picture, I guess, of some ideas, but I don't know. I haven't been able to like explore all these corners in as much detail, so maybe let me just give some kind of conclusion, I guess. So we have this idea of quantum chaos that we studied, and there are different probes for quantum chaos that people have looked at, and one of them that I was studying today is like sensitivity of eigenstates to external perturbations, which is captured by this fidelity susceptibility. We showed that sort of near the axis of the spectrum, this is qualitatively different from the interior in the sense that it's more rigid, and that sort of made us propose this sort of new universality class. And then if you look at the actual computation using the supersymmetry method that I sketched, you get an effective description for the UFL in terms of a supersymmetric and Savage model. In gravity, this is not accessible directly because if you look at the topological expansion, it doesn't contain the information of this Savage model. But instead, one requires a more complete description that we call universe field theory, and it has like branes and like open strings as well. And it turns out that a certain configuration of D branes actually gives me exactly this effective field theory that I want. So in that sense, you could say that this field theory sort of geometrizes certain aspects of chaos. But I think it's pretty cool because I think initially when people look at string theory, they don't necessarily think about it as a theory of chaos. But it turns out in the very late time regime, or in this case, like very much near the edge, this full like rich geometric structure appears. So there are other things you could do. So for example, there are
Topological strings.
Yeah, topological strings. Yeah, that's right. So there are other probes of eigenstate statistics that one can study. For example, inverse participation ratio is one, but there are many others in the chaos community. So I think that's very interesting for maybe people in our field to explore. Then there's the question of, we've studied now two-dimensional holography, but does the same thing happen in higher dimensions? Well, higher dimensions have new issues that don't arise, like for example, spatial locality, space-time symmetries. It turns out to be quite hard to actually define quantum chaos in those cases. So one proposal for two-dimensional CFTs that is quite interesting appeared recently, which I called RMT2. So one thing we were thinking about was maybe can we study this in like some model like that, I guess, where one has more control. And one of these models was Morgan Stanford Witten model that we have been looking at, that sort of looks a little bit like the SYK, but it has some different features. So but yeah, it's an emergent CFT in the IR, and it shows some kind of chaotic property. So it'll be interesting to see if we can sort of realize some of these ideas of chaos and like this effective field theory also in that context. Yeah, that's all I want to do. Okay, yeah.
I just have one more question is, when you show the airy action, let's say, for these soft nodes, are those soft nodes, can I interpret those soft nodes as me going from the IR, because you said the IR in the deep IR, here is conformal. Then you move to the UV, gradually, perturbatively, let's say. Can you say these soft nodes are fluctuations in that?
Yeah, that's right. But I think the UV and the IR here are kind of different from what you're used to in effective field theory. So if we think about effective field theories of chaos, the UV means that we're probing very small energy differences, while the IR is like large energy differences. So these these kind of like flavor theories, I guess. They arise as effective field theories for this energy differences. So when I take
So you mean IR? You mean long time?
Yeah, long time. Yeah, late time.
Small gaps.
Yeah, that's right.
Small gaps is late time physics.
Yeah, so late time physics, it's small gaps, so you're probing more of the and then of course these so initially you can approximate for short times, you can approximate it very well, but then of course when So I think it's a very, very interesting thing that people haven't like really, at least in our community, haven't really exploited that much. Because it's kind of a different way of thinking about effective field theory in this setting. Yeah.
Do you have an interpretation for matrix models more than one matrix?
That's an interesting question. I don't think we have addressed that at all in any of our works. So yeah, it would be definitely interesting to see. I know that there are some discussions of this in the context of like two-dimensional holography, for example. But to me, it's not clear how that would fit in here. Yeah.
Sorry, why did you say that? Isn't there like a way of thinking about GT gravity as a two matrix model?
Yeah, but I mean, I'm just saying like this framework.
Oh, this framework.
Yeah.
It fits more like in the context of ETH.
That's right. Yeah.
That's like generalized ETH as a multi-matrix model.
Yeah. So yeah, it's definitely been studied in the context, but I mean, I'm not sure we haven't studied it in this framework, I guess. Yeah.
Any other questions? I do have another question. So you have an expression for any M&N because this Kontsevich integral you could do.
Yeah. So you can
Very
take.
curious, yeah. What are these? Are these some ensemble integrals?
What do you mean by ensemble?
So what you did the Gauss GUE.
Yeah.
GUE for H and HA.
Yeah.
Whatever you called it, right? And then you got this expression which had, well, GOE, GUE, and the other one, like beta 0, 1, and 2.
Yeah, the symplectic.
So those are three ensembles that we do know and love.
Yeah.
Now you have an expression that matches this, but you have an extra parameter MNN, these extra parameters MNN that could vary.
Yeah.
And that are they telling you about other ensembles or these ensembles?
Yeah, I mean, there's definitely a structure here. So this is actually super interesting. I mean, so.
And what's so special about flavor 3 or 2? Like, there should be nothing special about that.
Yeah.
2, 3 branes. Why it's so special?
So we know that RMTs they're like universality classes, I guess. So there are 10 universality classes of RMT. They're called like Altland-Steinbauer classification. So it turns out that there is a similar classification from this perspective, and they correspond to different coset space. So they correspond to different symmetry breaking patterns, and they are each associated to different supergroups and different super subgroups that you break them to. And in that sense, I think the class. So maybe, I mean, this is not maybe answering your question exactly, but I think it is sort of touching upon it, because I think this sort of the different supergroups that I can have, you can classify the different symmetric spaces that I can obtain in this way, and those match precisely the 10 sort of universality class of RMT. So in that sense, there is some kind of like special groups.
Do you know of any other betas as something that people identified as a universal class?
I mean, they're usually parameterized by alpha and beta, right? So so you have the betas, and then there's like alpha.
Right. Yes.
Yeah, and I think those 10 cases correspond to 10 symmetric spaces that are sort of cosets of supergroups. So yeah, but I mean.
Okay.
Yeah.
Thank you so much. All right. Last time. Yeah, thank you so much.
Yeah, no worries.